Okay, we're going to look at lecture 7 of this vector algebra section of the module. We're going to look at vector equation of a plane. We've done the vector equation of a line, but we'll get a recap of that. We're going to look at the Cartesian form, and we're going to look at some various examples, including intersection of lines and planes. Learning outcomes for this set of slides. We're going to see how we can construct the equation of a plane in 3D using vectors. We'll use the laws of vector multiplication. We'll actually be using the cross product, but we'll also use the dot product in one of the calculations where we look at intersection of a line and a plane. We'll see the equation of a plane in vector and Cartesian form. We'll compare that with the intersection with the equation of a line, and then we'll see how these our line can intersect with a plane and work out the points of intersection. And we'll look at in another example of the distance from a certain point to a plane and find that shortest distance. Right, we're going to look very briefly at a recap of the equation of a line in vector form. So we have a line that we're trying to find the position vector of any point on it, and that general point we're going to define was this point P, which has a position vector R. So we want to find R equals. That's the objective. Now we have 2 points on the line, and using those 2 points we can define a vector in the line. So that a vector in the line will be a to b, which will be minus a, b. Now the position vector of any point in the line can then be said to be a, the position of a, plus some multiple of the vector ab. So would be along there. So that is the equation of a line. A, the position vector of a known point, plus some multiple of a vector in the line. We can rearrange that equation to be a different format, and this is for an infinitely long line. In Cartesian format, we change the R to x, y, z, and the B's and A's to be A1, B1, A1, A2, A3, B1, B2, B3, and we manipulate the 3 coordinates to be all equal to t. So that's the usual common format for equation of a line. There's one caveat with these, and we need to just understand that when we the denominator is 0, the number at the bottom is 0, so physically the numerator would always be 0. So, but if we're doing any say programming of these calculations, we need to explicitly set that. We're going to now look at the equation of a plane. So if we have a normal vector to a plane, then that can define the orientation of a plane. That normal vector also could define a plane at any point. Now I'm moving it along a line here, but because that plane is normal to that vector. But if we have a single point within the plane, say A in this case, then we've defined the position of the plane and the orientation. And in fact, that is what we need for definition of a plane, a normal vector and a point. So this slightly obscured slide here. A normal vector and the coordinates of one point will uniquely define a specific plane. We can do that if we look at our construction similar to a line, where we have a line joining A and P, and in this case is A and P are 2 points in a plane, in the same plane, and we can draw a line from A to P, so that line AP will be in the plane, and AP is minus AR, and we have a normal to that plane. So two things we've got one line in the plane, AP, and one normal to the plane. So our AP is written R minus A. So definition of the plane is simply this: Rn equals R dot n is equal to A dot n, or R dot n is equal to P, a scalar. Remember, this dot product is a scalar, produces a constant number, and R, we don't expand that because R is our general x, y, z coordinates in Cartesian. So that is the equation of the plane. Well, those two are same format, different formats of the same equation for equation of a plane. We can expand this into Cartesian formats. Now n is n1, n2, n3, and R is x, y, z, so it's simple multiplication by the dot product, and we get the Cartesian form for equation of a plane. Let's have a look at a fairly standard example for equation of a plane. So find the equation of a plane through the points A, B and C. Now any plane can be uniquely defined by 3 points in space. Any plane can be uniquely fitted to 3 points in space. And we're going to find the equation of that plane in vector and Cartesian format. Now we require a line and a normal to the plane, but at this point we're going to take the two vectors in the plane. Now two vectors in the plane will be any two lines joining these 3 points. Now you can see that you can get 3 points, so we just put 3 lines, but we only need to choose 2, and then we need a normal. And so A minus B lies in the plane, A minus C lie in the plane, which we can calculate those two. Now how do we get a normal to two lines? Well, the cross product or the vector product, same thing, give us a normal. They give us, remember the right hand rule, whereas if our first finger and second finger are vectors, then the thumb is the normal to those two vectors. So first finger and second finger are A minus B and A minus C respectively in this case, and the normal will be the thumb. So we just do the cross product, and I'm expanding it here using the determinant form to give this vector. So that vector is normal to the plane. So we've got a normal to the plane. We've got a point in the plane. In fact, we've got 3 points. We only need one of those 3 points. So we've almost completed this equation of the plane. Here's the equation of the plane. We choose R times the normal is equal to A point times dotted with the normal. And this one gives gives us 15. There's an equation of the plane. We could have used, in this place, a different point, one of the other, B or C, but we've used A, and it would give 15. In component form, we just replace the R by x, y, z, dot it with the minus 1, 9, 11, the normal. You can expand that, and there it is, the equation in Cartesian form for the plane. We can check by the 3 known points that this works. We put x, y, z for either A, B and C. So for A, it comes out to 15. For B, we're putting in 1, 3 and minus 1, that comes out to 15, and C we put 0, minus 2, 3, and that comes out to 15. So a little check there you can do when you're working out the equation of a plane. Here's another example. You might want to try this before I explain it, but I'll now explain how we get to this. It's exactly the same as the last question. We've got 3 points that lie in a plane, so we want to find the equation of the vector equation of the plane through these 3 points. We need 2 vectors, so we can do P minus Q, Q minus S, or P minus S, or in fact the other way around, it doesn't really matter. So I'm doing Q minus P and S minus P for this example. So I get 2 vectors. We do the cross product. Here's the cross product expanded as a determinant. Further, and the normal is 1, 0, minus 1. So simply we write down the cross product of R times that normal is equal to a point in the plane times this normal, dotted with this normal, scalar product with this normal, which in this case comes out to be 0. In component form we can just replace R with x, y, z vector as the Cartesian form or component form. That's expanded to be just z minus x minus z is equal to 0. So in fact this plane is y equals 0, so it's in the plane, in the xz plane. Let's have another example to go through. Lines and planes. Find the point where the plane meets the line. So we've got 2 vector equations, one of a plane and one of a line. Expanded the vector 1 into a Cartesian form. We don't need to. So a vector equation of the line, and in this one we want R to be equal to R. So we could just substitute this R into this dot product and do the calculation. Second part of this question says find the angle that this line intersecting with the plane makes. So part A is simply we replace this R in the plane equation with this R from the line equation. So it's where the same point x, y, z are equal. So we've got 2 equations, we sub 2 into 1. Is explicitly done here, and we just expand that. It's quite straightforward to do it in a dot product way, and it comes out to be 3 plus 5t equals 4. So t in this case comes out to be 1/5. So we can simply write down the equation of the line and get with the t of 1/5 and get the coordinates x, y, z. There we are. These are the coordinates of the point where that line crosses that plane. Let's find the angle that this plane makes with the line intersecting it. So we've got the dot product. So we've used the cross product, the scalar product previously. We're now we used the cross product previously. Now we're going to use the dot product in concern with the line. So the dot product of x times y equals modulus of x, modulus of y cos theta. We have a normal to the plane, and we have a vector in the direction of the line. We were given that. That's the what's in the brackets after the t. So we've got 2 vectors. Now it says what's the angle with the line and the plane. It doesn't say what is the vector the angle with the line and the normal to the plane. But we have a vector normal to the plane, so that's the convenience. We use this, we find the angle between these two, and then that angle must add up to 90. So we just dot product these, we get a value of 5, and then we say that 5 is equal to that right hand side of the dot product, and these are root 6 and root 6, so that comes out to be 6. So we divide the 5 by 6 and we get an angle of 33.6 degrees between the line and the normal to the plane. So we need to add that up to 90, so the angle between the line and the plane is 90 minus 33.6, which is 56.4 degrees. Let's have a look at one more example of lines and planes. And this is quite interesting. We have a point in space and we want to find the distance of that point from the plane. The distance, the shortest distance, and the shortest distance is a normal from the plane through the point. So we need to find the equation of a line going through the point with a vector of that line equal to a normal to the plane, and we have a normal to the plane in the definition of the equation of the plane. So we can look at this equation of the plane and we see that the normal in that plane is 1, 2, 2. So that will form our equation of our line going through the point P, which is 2 minus 3, 4. So the equation of the plane in vector form, we can write that instantly based on the Cartesian form. The vector normal to the plane is 1, 2, 2. Vector equation of the line is that format. So if it's going through P and OP is 2, 3, 4, then the vector equation of the line is such. We can work out now the equation of the plane, of the point where the line intersects the plane. As we did in the last example, we simply substitute r into the plane equation and calculate the value of t. Comes out to be t equals 1. We put 1 into the plane, into the line equation to get the coordinates of the line where it crosses the plane. So this is a line normal to the plane where it crosses the plane at 3 minus 1, 6, and it goes through the point P at 2 minus 6, 8. So now we've got 2 points in 3D geometry, and all we need to do is work out the length of the line between those 2 points, and that's simple Pythagoras 3 and 3 with 3 components. So 3 minus 2 squared minus 1 plus 3 squared, 6 minus 4 squared, all square rooted, comes down to 3 units, because we weren't given any dimensions, any units, meters, etc. One further example on lines and planes. But first of all, just think about what we can do with intersecting planes. So if we have 3 planes intersecting, then they may intersect like this at a single point, and then we say we've got a unique solution. They may intersect like these 3 here, or these 2 here, whereas along the line here we've got an infinite number of solutions. We've got an infinite number of solutions here. These 3 don't appear in the picture to be interacting, but say they were all in the same plane, again with the infinite number of solutions. So we have to be careful about whether we've got infinite number of solutions and what it means, or a unique solution and what it means. These diagrams of planes not interacting, those 3 clearly not interacting, those 3 clearly not interacting, there's no solution. for the three interacting planes. In this case, we've got three interacting planes, but two of them are parallel and not the same plane. So there's no solution to the intersection of these three planes. These three planes intersect in a triangle form like this. A line in each of those are parallel. So we have to be a bit careful if we're looking at intersection of planes. And we're not going to go into the detail of intersection of planes and the various options. However, it's good to be aware of these types of intersections, interactions, and how many solutions you would expect. We are just going to do a quick example of intersection of two planes, and we're going to find the line of the intersection of the two planes. So it's more like this, or like the intersection between these two here, or indeed the intersection between two of these here. Okay, and it's the equation of this line that we're interested in. So we've got two planes in Cartesian format. In vector form, they're clearly r dot 111 equals 5 and r dot 412 equals 15. The line of intersection is perpendicular to both vectors. So we've got two vectors that are normal to these two planes. If we find a line that is perpendicular to those, that vector is in the direction of the line of intersection. So we take the two normal vectors and we cross those. Alright, so let's just go through the cross product of these. And here we have the determinant form, practice doing this. And we get a vector 1, 2, 3 in this case, which is a vector in the line of intersection of the two planes. We need 1 point on the plane, and we can choose any x, y, z. It's convenient to choose one of them 0, and why not choose x equals 0? So we're choosing x equals 0. So 1 point in the plane, we put x equals 0. These are the two equations. But x equals 0, so the equation is going to be x plus z equals 5 and y plus 2z equals 5. Yeah. We simultaneously solve those for x and z. Comes out to be y and z. So y equals minus 5 and z equals 10. So 0 minus 5, 10 is 1 point in the plane. In the two planes and on the line of intersection. Therefore, equation of the line is 0 minus 5, 10 plus t times the vector in the that we just got from the cross product of the two normals. So that's the equation of the line of the intersection of two planes. Okay, here's some questions, further questions. This is from exercise sheet 2, question 3. Find the vector equation of the line joining the points P and Q, as shown there. I'm just going to go through, find the vector equation of the plane through 3 points, A, B, C. And the question is linked to P and Q, so I'll show the normal to the line P and Q is, so the line P and Q is normal to the plane through A, B, C. So we'll see that that forms a vector normal equal to the plane's normal. Find the point of intersection of G of the line on the plane through ABC and verify that that G is the centroid of the triangle ABC. So we're going to look at 2 points here, AB and AC, and do the cross product of those. We can go through the steps, do the cross product, and we can calculate our equation through the plane ABC. And that comes out to be equal to 7. So we've got our normal. Here, I'll drop this 6 here because it's still a normal if it's 2, 3, 1, a factor of 6. So I've not included that in this expression here. We can write that out in Cartesian form. So there's the equation of the plane again, going through 3 points A, B, C. This vector is parallel to the normal. I've simplified that. So this vector is parallel to the normal. Point of intersection G between the line through PQ and the line through ABC is this equation. And the plane R equals 1 minus R dot 213 equals 7 are equal. So we're going to substitute that R into the plane equation, and we get T equals 1 and the intersection point is then 1 minus 1, 2, by substituting that into the equation of the line. Midpoint of H equals AB. Midpoint H of AB, well, we can find that because by putting T equals to 0.5, so we get this vector is a midpoint of the line. HG is the distance from G to this point. That's the modulus, so it's 1 squared plus 1 squared plus 2 squared, square rooted. So 1 times 0 squared plus 1 squared plus 2 squared, so root 5. CG is 2 root 5 in that case, because it's twice that length. Key points then. Vector notation, the equation of a line is given in terms of a position vector, A, plus and a general vector in the direction of the line. And we usually find that from 2 points, so B minus A for example, and a multiple T which can take any point. The equation of a plane is given in terms of a line in the plane and a normal vector to the plane. But in fact, where we see it is a point times a normal is equal to a constant.